So, what did we learn in the first part of the course? About ODEs, we saw the characteristic equation method, the method of undetermined coefficients, and the power series method. And then for partial differential equations, we saw the method of separation of variables. And well, before that, we saw periodic functions, even and odd functions, Fourier series representations, and that's it. So, what are we going to learn now? We are going to learn another method, another technique to solve partial differential equations, which is again related with Fourier, but before we had Fourier series representation, so the important one is this one, series. And now we will have Fourier integral representation. Okay, so that would be the difference between the method of separation of variables and this new method that we are going to see now. Sorry, in this lecture we are not going to see the method itself. We are going to introduce the Fourier integral representation, which are the new main offshoot of this method. Okay, so taking in mind that our intention is use this Fourier transform, that, okay, this is another word that we will see in the next lecture, to solve partial differential equations. Okay, so today we are going to focus on Fourier integral representation. So forget about partial differential equations and forget about this word transform. So, baby step first. Fourier integral representation. Okay, so before we used Fourier series to solve boundary problems over intervals. And these intervals were bounded regions, okay? So now we are going to see or to use Fourier integrals, our new main element of the lecture, to solve boundary value problems over unbounded regions, such as the infinity line, like the whole R. Okay, so this is our situation today. We are going to see Fourier integrals, having in mind that we were going to use these guys, or kind of these guys, to solve partial differential equations in unbounded regions. Okay, so with this in mind, recall some stuff of the first part of the course. For a 2p periodic function f, we have the Fourier series representation that we can write in this way: a0, this an, and this cosine, and this sine, and this bn. And we have the Euler's formula, if you remember. So here is how we compute a0, and here is how we compute an, and here is how we compute bn. Okay, so usually, so this in this situation we had a function f defined in an interval of length 2p. Okay, and then we repeat this graph and this definition because it's periodic, so we were repeating this function outside this given interval 2p, and that's how we get the whole graph of the function f, let's say. So now the situation is, okay, forget about that interval and that period and that property of being periodic, and now imagine that we have our f given, defined in the entire real line, so in all r, okay? And okay, let's say that it's not periodic, otherwise we go back to the previous case, to the previous setting that we already know how to deal with. So we want, if we are not periodic, so we are in this new situation, we won't have a Fourier series representation, but we do have a Fourier integral representation. So let's see what that means. So for f piecewise smooth on every finite interval and verifying this condition, again, don't worry about these assumptions. During the course, we are going to work always with this type of functions. You don't have to check if the function verifies this, but it's good to know that there are some assumptions. It's not that for any function we will have a Fourier integral representation. So we do need these two guys, these two assumptions, piecewise smooth on every infinite interval, and this, which means that, okay, f is integral in some sense. That, again, we are not going to give the formal definition. Okay, if we are lucky and our function f verifies these conditions, then we claim that we can claim that f admits a Fourier integral representation. This is the new word. Remember, we are going to make difference between series and integral. And this is the representation. It's the integral from 0 to infinity of, we have these guys, this is a function a of omega, and it kind of plays the role of this an that we had in the past, because this function a of omega is next to this cosine here. And again, look, this is omega, and this is omega, and this is omega, and omega takes any value from 0 to infinity. So we are not anymore in this discrete case where we have this an and bn, and this n was a natural number, like 1, 2, 3, and etc. So now we are really enlarging the range of what we are looking for, okay? But it's quite related to the previous setting in the sense that, okay, we have a function next to a cosine and a function next to a cosine, and these functions do not depend on the variable x. So they kind of play the role of an and bn, okay? And we tried to explain that a little bit. We are not going to give a lot of details because it won't be important for you to know how we deduce the Fourier integral representation from the series one, but okay, just to have an idea, we can talk a little bit about it. Okay, so this function a of omega, we can compute it as this integral 1 over pi, and the integral between minus infinity and infinity of f of x cosine of omega x. And here is also clear why we have this analogy between this function f of omega and the coefficients of a Fourier series representation an, because if you remember, there was a number there in Euler's formula, the function f, but the integral like between minus p and p, where 2p was the period of the function, and a cosine, but with some n and p here. So they are quite similar but different, okay? And this omega goes from 0 to infinity. And again, now we have the formula for the function b of omega, which has the same factor in the front. And here we have these improper integrals that we saw in the auxiliary notes. So that's why we mentioned them in the notes. And we have the f times the sine of omega x. Okay, so this is our new situation. This will be our Fourier integral representation of a function f. And here we have the formulas to compute this function a of omega and b of omega. Okay, so, and we have again this kind of property. When the function f is continuous at the point x, we have that this Fourier integral representation coincides with f of x, and when f is discontinuous at the point x, then we will have again this average of the right and left limits. So we still have this property in this context. So in other words, we have these two identities. F of x is exactly this Fourier integral representation when f is continuous at x. So here we have our new functions, a of omega and b of omega. And we have this average here of the right and left limits when f is discontinuous at x. Okay, so some properties and differences between these guys, the Fourier series representation and the Fourier integral representation. So first of all, here we have like a discrete setting because of this value and a sum because of these values n equal to 1, 2, 3, and so on. And here we have the whole range from 0 to infinity, and instead of a sum, we have an integral, okay? So that's what I just said, the discrete Fourier coefficients, because we have these a0, a1, a2. So a0 was the guy like just isolated, that number floating around. And then a1, a2, and so on were the guys next to the cosines function, and b1 and b2, well, here it should be a 2, and etc. were the guys next to the sine functions. And here we have continuous Fourier coefficients. We only have these two guys. Let's say that this kind of a0 disappeared in some sense, and we only have this a of omega, which is next to a cosine function, like only one, and this b of omega, which is next to a, when I say next to, I mean multiplied. It's multiplying a sine function in the case of b and a cosine function in the case of a. Okay, so again, discrete, meaning that we have these values and natural numbers. Continuous, meaning we have this range of values from 0 to infinity. Okay, and then here the function f in principle was defined in on an interval minus pp, and then we have a periodic function, so with knowing the function in this interval of length 2p gives us the information about the whole function, because we just copy that graph outside the interval. And in this case, we have a function f defined in all R. Okay, so this condition that you don't have to check it in each exercise can be expressed as f is integral on the entire real line. Okay. Okay, now we are trying to give some ideas of how we can deduce, let's say, the Fourier integral representation from the series one, but okay, you can skip this part if you want. Okay, so we can think about these two guys, a of omega and b of omega, as limits of an and bn when p goes to infinity. Okay, makes sense, because if we have a function defined on minus pp and then we make this p goes to infinity, we will have a function defined in the whole real life line, or no? So makes sense, at least the idea. Let's try to see if we can, if we can give an idea. Okay, for a0, let's see that goes to 0, because this a0 guy doesn't have a representative in the integral Fourier integral representation. So we should check that this guy goes to 0. So a0, if you remember the definition in the Euler's formula to compute a0 for a 2p periodic function, we have this guy. So if we put absolute value, we have this inequality where the absolute value goes inside of the integral. And then, okay, the integral of a positive function in this, over this tiny interval, let's say minus p, for sure is less or equal that considering the same function but in the whole line, like from minus infinity to infinity. So we have this inequality, and then by hypothesis we know that this guy is finite. And then, so this is just a constant, let's say, and doesn't depend on p anymore. And then we have this factor here. So when p goes to infinity, this guy goes to 0. Okay, which I guess is what the next line says. Exactly. So we get this 0 guy. And this is why in the Fourier integral representation we only have this a of omega and b of omega, and we don't have something like capital A0 of omega. Okay, that was the easy part. Maybe for this an and capital A of omega you need to pay more attention, but again, don't worry, because we are not going to, this is not important for solving the exercises. It's just if you are curious to know how we can prove it. Okay, so this is our old setting for series. We have this coefficient an, and if you remember the Euler's formula, is exactly this guy for the 2p periodic function. And this is our new setting, capital A of omega, which is the integral for minus infinity to infinity of f, and this one function, like one cosine of omega x, and this factor is 1 over pi. Okay, so how to go from here to there? We are trying to go to give you an idea. So we start with our an, and we can say, so this is just, you have to believe me, we can say that, oh well, this p here, we can take the limit to infinity, so we kind of have this guy here, minus infinity and infinity, but we still have this guy inside the cosine, n pi over p. Well, and to try to be similar to this function capital A of omega, we multiply and divide by pi. So now this guy here is capital A in this particular omega n. Okay? So this, exactly this, with this omega n pi over p. So what we have here is pi over p and this value. And if we think about what this guy is, pi over p, and you remember this definition that we gave here with this notation, let's say not definition, this notation, omega n equal to n pi over p. If we take two consecutives n, like n plus 1 and n, this omega n plus 1 minus omega n is exactly this value, pi over p. So what we are having here is the function capital A in this omega n times this distance. So we have the real line, the positive real line, divided in a couple of, well, not a couple, like infinity intervals of this measure, this length, pi over p, and we compute like this the value of capital A in this omega 1 times omega 1 minus 0, A in this omega 2 times omega 2 minus omega 1, and so on and so on. So this is the situation, and this is what we have here. And okay, so finally, this part of the Fourier series representation can be rewritten, let's say, in this way, where you have to believe it's a couple of steps there, like this sum from n equal to 1 to infinity of this capital A in omega n cosine in this particular omega n times x, and this value, which can be written like that, but remember that it's just pi over p. Okay, once we have this expression, for those that know about what the Riemann sum is, it's exactly what we have here. So taking the limit, or like this series is, taking the limit, let's say we get this integral. So the integral from 0 to infinity of our function capital A of omega and times cosine of omega of x, differential x. Okay, so just last comment, imagine that we have this situation and we have this infinity amount of values of omega n, but then when p goes to infinity, this length of the intervals goes to 0, and that means that we are having more points, and we have an enormous amount of points in such a way that at the end we are considering all the real line, the positive real line, and that's why we can jump from the sum to the integral. Okay, so I hope this idea is clear, and if it's not, don't worry about it. It's just for those that are curious how to jump from the series to the integral. Okay, so we cover, in the limit we cover all the values of omega. That's what I was trying to say. Okay, and you can imagine that it's similar for Bn. We go to it's exactly the same, but instead of a cosine function, we have a sine function. Okay, just that was an idea. Example. Find the Fourier integral representation of this function f of x equal to 1 if x is between -1 and 1 and 0 otherwise. Okay, so we know that the Fourier integral representation is given by this formula, where we have this capital A of omega and capital B of omega instead of these coefficients that we had before in the series, and we have this integral from 0 to infinity, differential of omega, and we have this cosine of omega x, sine of omega x. So this is our new favorite element of the lecture, let's say. Okay, and x now is in the whole R, because now our function is defined in the whole real line, R. Okay, and it's not periodic. And we have these formulas here to compute the function capital A and capital B, which are super similar to the Euler's function formula, the differences are the factors in the front, which now we have 1 over pi, and we do not have proper integrals, we have improper integrals of this type, minus infinity, infinity, and yeah, we only have these two functions instead of infinity values with this n variable. Okay, so we need to compute these guys. Let's start for capital A of omega. By definition, our formula, we have that this is 1 over pi, and this integral from minus infinity to infinity of f cosine of omega x differential x. Okay, but now, in this example, our f, it's 0 if we are not in the interval minus 1, 1. So, this minus infinity, infinity just turn into minus 1, 1. That's nice in this example, at least. And the value of f of x in that interval is just the number 1. So this is like a first easy example. And we have cosine of omega x here. Okay, so we have to solve this integral. An antiderivative of this integral is sine of omega x divided by omega, and we can do that if and only if this omega is not 0. We cannot have this expression if omega is not is equal to 0. So okay, and we have to evaluate this between 1 and minus 1. So finally what we get is this expression. 1 over this factor was always there in the front, and then we have this expression. And remember that sine is an odd function, so this minus here goes outside, let's say. And finally what we get is this expression, 2 times sine of omega over pi omega. And this is okay for every guy that is not 0, so omega positive. And but our range of omega is the guys greater or equal than 0, so we wonder what's going on in 0. And remember, in the auxiliary notes we saw this L'Hopital rule to compute some limits. So, well, this was the conclusion that I was saying, that we have this identity when omega is greater than 0. And now, what's going on for 0? So, let's take a look at this limit, which is a piece of this expression, because this 2 is okay and this pi is okay, but this guy is not okay. Let's say when we want to evaluate this guy in omega equal to 0, we are not allowed. So we wonder what's going on. Okay. So this guy, omega goes to 0 when omega goes to 0, it's clear. And sine of omega goes to 0 when omega goes to 0 as well. So if you remember L'Hopital's rule, we can apply it, and what L'Hopital's rule says is like, okay, you can differentiate like the function here up, the function that is here, and the function that is under like the division, this quotient, and then compute the limit. So when we differentiate these guys, we have cosine here and 1 here, and 1 is nice because it's just a number. And now when we compute this new limit, this auxiliary limit, cosine of omega when omega goes to 0 goes to 1. So we this auxiliary limit with the derivatives exists and gives us this 1. So this rule, L'Hopital's rule, says, okay, then your original limit is 1. So what we obtain is that this expression, when omega is 0, which is not true that we are going to say like, oh, when omega is exactly 0, what we mean is like, okay, when omega goes to 0, this function takes this value, 2 over pi, because we just saw that this piece of function goes to 1 when omega goes to 0. So this is how it's formally and rigorously correct to write, but we can write here in this course informally. Just remember, we will write this guy, a of omega equal to this function that we found, for every omega greater or equal than 0, but remember that we mean with this that when omega is exactly 0, we take the limit of omega going to 0 of this expression. Okay, it's not that we can evaluate this guy in 0, is that this expression is well defined when we take the limit of omega going to 0. Okay, so that's for the first function a. Let's compute b. So for b we have this definition again, same factor, 1 over pi in the front, the improper integral from minus infinity to infinity of f of x, and the sign of omega x. And again, now we use the definition of the function, which makes this minus infinity and infinity goes to minus 1 and 1, and the value that the function takes in that interval is just 1. So we have this other integral, and now we are lucky because, okay, the function sign is odd, and we are in a minus interval, like minus 1, 1 in this case, so this integral is just 0. So b is 0 for everyone and every value of omega. Okay, now, finally, the Fourier integral representation of our function x, like 1 in minus 1, 1, and 0 otherwise, is given by this general Fourier series representation, where we already compute this a and this b. So we found that b is 0 and a is this guy, 2 sine of omega over pi omega. So finally we get this expression. Okay. Now, just a remark. Observe that this function f of x, our function 1 in minus 1, 1, and 0 otherwise, is continuous for every x that is not exactly minus 1 and 1. So if we see the graph of this function here, so the function in the open interval minus 1, 1 takes the value 1, and for the rest of the guys it's 0. Okay, so for this open interval here and open interval here and this open interval here, the function is continuous, so we will have that this Fourier integral representation coincides with f of x, and these two guys, minus 1 and 1, are the points of discontinuity of x. So there we will have this that the Fourier integral representation coincides with the right and left limits, which in case of minus 1 is 0 plus 1 over 2, so 1 half, and for 1 is 1 here and 0 here over 2, so again 1 half. Okay, which is written here. Okay. So we know that the Fourier integral representation of x coincides with f of x when f is continuous at x and takes the average of the right and left limits at points of discontinuities. Then we have exactly this formula here, let's say, the Fourier integral representation will be exactly f for every x with absolute value different from 1, and this average for 1 and minus 1, which is 1/2. So we have this. Now, if we remember the definition of f, which is just the constant 1 in the interval -1, 1, and these guys for 1 and -1 we saw that are 1/2, and then the function is 0 otherwise, we have this other identity. So this improper integral is 1 in this case, 1/2 in this case, and 0 otherwise. Okay. So one application of this Fourier integral representation is that we can compute values of improper integrals just knowing that these guys are the Fourier integral representation of some function f. Okay, that's an application. And we have something similar that we had before with Fourier series representation, where we knew that, okay, if I have a 2p periodic function and I know something more, like, okay, the function is not only periodic, it's also even, then we knew that the bn were all equal to 0. Well, we have exactly like the analogous thing here. If we know that f is even, then our function b will be 0, and if we know that f is odd, our function a will be 0. Okay, as we saw in this example. Okay, so advice. Remember that I also gave this advice for Fourier series representation. If you have to find the Fourier integral representation of a function f, it will be always useful to check if f is even, odd, or neither. So this first step will simplify the computation of the Fourier integral representation, because just if we are lucky and we have an even function or odd function, I only have to make one computation, capital A of omega or capital B of omega. So that's my advice. Try to follow it if you want. Okay, so Fourier series, like in the past, the previous lectures, representations can be used to compute series, like we did in this assignment. In the assignment 1, exercise 2.2, we used Fourier series representations to compute, for instance, this series. Okay, so Fourier integral representation can be used to evaluate some improper integrals, and that's I was talking about a couple of minutes ago. So let's see an example. Same function, because we already know this Fourier integral representation, and we just saw that this improper integral is equal to 1 if x is between -1 and 1, and is equal to 1/2 if we are -1 or 1, and is equal to 0 otherwise. Okay, so if we choose x equal to 0, which verifies absolute value strictly less than 1, so we are in this case, we know from this identity, this huge identity that we have here, that 2 over pi integral from 0 to infinity of this sine of omega over omega divided by omega, and here we have x equal to 0, so here we get that since cosine of 0 is equal to 1, this guy kind of disappears in the sense that it's equal to 1, and we are in this case, as we saw. So what we have is this identity here, which means exactly that this improper integral from 0 to infinity of sine of omega over omega takes the value pi over 2. So that was all for it. So we saw in the definition of Fourier integral representations, and which involved these improper integrals that you can see the auxiliary notes for this lecture to see the definition. And we compute these coefficients capital A of omega and capital B of omega that are involved in this Fourier integral representation, where we gave the differences that we have between Fourier series representation and Fourier integral representations. And we of course have similarities in the sense that we still have this type of properties where, okay, if I'm working with the even function, one of these two guys disappear. For even functions, the v, capital V of omega is 0, and for odd functions, capital A of omega is 0, and we still have this property about when f is continuous at some point, then this integral Fourier representation coincides with f, and when f is discontinuous at some point, then we have this average again. So these are similarities that we have with the previous setting. And the last thing we saw is that we can use Fourier integral representations to compute the value of some improper integrals. And this is the analog with the series representation when we were computing series. Okay, when we used to choose one particular value of x, and that gives us the value of a series, where here we are choosing a particular value of x and we can compute these improper integrals. And that's it for today.